Hi, my name is Anthony Ruth. We're going to learn about Gauss's law today. Gauss's law allows us to find electric fields without the need to integrate. We can also use Gauss's law to find voltages, and we'll see that later. Prelude to Gauss's law. We have a ring with a charge Q on it, and we want to find the electric field at a point P inside the ring. We can see from symmetry that the electric field in the y direction cancels out. To find the electric field in the x direction, we can integrate around the whole circle. What we find is that since electric field is proportional to the inverse square of the distance away, the smaller, closer charge on the blue part of the circle cancels out with the larger but more distant green part of the circle. The electric field at the point P is 0. Since a donut is just a bunch of rings added together, we get the same result for a donut shape. In the previous slide, we found that charge anterior to the point cancels out, and only charge on the inside counts. With this knowledge, we introduce a new quantity called flux, which is proportional to the interior charge. Electric flux equals Q inside over E naught. And E naught is equal to 8.85 times 10 to the 12th farads per meter. We can now write Gauss's law in its full form. Electric flux equals Q inside over E naught equals electric field perpendicular to the area of the Gaussian surface. To solve a problem using Gauss's law, we construct a surface such that the electric field is constant on the surface and the electric field is perpendicular to the surface. That means that the electric field lines will point perpendicular to the surface. We can find the electric field if we know the area of the surface and the charge inside. Gauss's law sphere. For a spherical charge, the Gaussian surface is another sphere. I've drawn in the electric field lines. If the sphere has a charge of Q, and the Gaussian surface is a distance r from the center of the sphere, Q inside equals Q, and the surface area equals 4 pi r squared. First, the electric field equals Q over E naught 4 pi r squared. For a spherical charge, the electric field is the same as Coulomb's law. Gauss's law line. For a line of charge, the Gaussian surface is a cylinder. To find the area of the surface, we only count the cylinder itself. The two circles on either end cannot be part of a Gaussian surface because they do not have a constant electric field, and the electric field is not perpendicular to the circles. Q inside equals Q, surface area equals 2 pi RL. The electric field equals Q over E naught 2 pi RL. Gauss's law block. The block has two sides of length L and a third side of length D and a charge Q. We want to find the electric field at a point P, which is facing the square side of the block. We have to account for the area of the square that P is on and the other square opposite of P. Q inside equals Q, and the area is equal to 2L squared. The electric field is equal to Q over E naught 2L squared. Symmetry. The Gaussian surface must have a constant electric field. To find the electric field at a point P, which is inside the block of charge, we have to place our Gaussian surface so that on each side it's the same distance away from the edge of a block. Making our Gaussian surface this way accounts for the fact that the charge to the left and to the right of the surface. Complex problems. We often encounter complex problems that can be broken down into the parts we have used so far. Consider an infinitely tall and infinitely long block with a width d and a charge density j. The block has a spherical hole in it of radius s. We will split this problem into the square and sphere we already derived. We will cut off a chunk of the infinitely tall, infinitely long block to use the equations we derived before. E equals Q divided by E naught 2L squared, where Q is equal to the charge density times the volume of the block, which is Q equals J L squared D. Now we have the electric field due to the block. We will subtract the electric field due to the spherical hole. Electric field equals Q divided by E naught 4 pi r squared, where Q is the charge density times the volume of the sphere. We represent the charge as being negative because a hole in a positive charge acts like a negative charge. Q is equal to minus J times 4 pi s cubed. And the final equation for the electric field equals J d divided by 2 E naught minus J times 4 pi s cubed divided by 3 times 4 pi E naught r squared, which simplifies to J d divided by 2 E naught minus Js cubed divided by 3 E naught r squared. Calculating voltage. Electric field is the gradient of voltage. We can quickly use Gauss's law to determine voltage. To the left is a central sphere with a charge 3q, surrounded by an empty space, and which is surrounded by a shell of charge 2q. The sphere and the shell are both conductors. The negative charges on the outside rearrange themselves to cancel with the positive charges in the middle. All charges end up on the surfaces of the conductors. Suppose we want to find the voltage at R is greater than R3, R3 is greater than R is greater than R2, R2 is greater than R is greater than R1, and R1 is greater than R. We can solve this problem easily with Gauss's law. We know the electric field inside a conductor is 0. First, we'll find the electric field in each region, then integrate in from infinity to find the voltage in each region. For R is greater than R3, the charge inside is Q. That's 3Q minus 2Q. So the electric field is given by Q divided by 4 pi E naught R squared. For R3 is greater than R is greater than R2, we are inside the conductor, and the electric field inside a conductor is 0. If we look at the way the charges rearrange themselves, we see that the 3Q on the inside cancels out with the minus 3Q on the inside surface of the shell, and Q inside is 0. For R2 is greater than R is greater than R1, the charge inside is 3Q of the central sphere, which gives us an electric field of 3Q divided by 4 pi E naught R squared. And of course, for inside the central sphere, the charge is 0 because all of the charge is on the surface of the sphere, not on the inside. And the electric field is Now that we have the equations for the electric field in each region, we're going to calculate the voltage in each region. We know that the voltage at infinity is 0. We declared the voltage at infinity to be 0 because it makes a good reference point for us to determine all other voltages. For R is greater than R3, we have the voltage equals minus the integral from infinity to R of Q divided by 4 pi E naught R prime squared dr prime, where I've substituted in R prime for R for the purpose of integration. This is equal to Q divided by 4 pi E naught R prime, evaluated from infinity to R, which is equal to Q over 4 pi E naught R. For the voltage inside the conducting shell, we have the voltage anywhere inside the shell is equal to the voltage at R3, because the shell is a conductor and has an electric field of 0. So we're going to use the equation for R greater than R3 to find the voltage at R3. And we get Q divided by 4 pi E naught R3. And of course this is also equal to the voltage at R2, which is on the inside surface of the shell. Now for R2 is greater than R is greater than R1, we have to add the voltage at R2 to the integral of the electric field from R2 to R. The expression we get is minus the integral from R2 to R of 3Q divided by 4 pi E naught R prime squared dr prime plus the voltage at R2. This is equal to 3Q divided by 4 pi E naught R prime, evaluated from R2 to R, plus the voltage at R2, which is equal to 3Q divided by 4 pi E naught R minus 3Q divided by 4 pi E naught R2 plus Q divided by 4 pi E naught R3. We notice that if we substitute in R2 for R, the first two terms cancel out, and we're left with only the third term, which is equal to the voltage at R2. Now for R1 is greater than R, we're inside the sphere, and the voltage anywhere inside the sphere is equal to the voltage at the surface, which is at R1. So we have the voltage at R1, or anywhere in the sphere, is 3Q divided by 4 pi E naught R1 minus 3Q divided by 4 pi E naught R2 plus Q divided by 4 pi E naught R3. You get this expression by substituting in R1 for the last expression we got for R2 is greater than R is greater than R1. And of course, this is also equal to the voltage at the center of the sphere. Actually, it's equal to the voltage anywhere inside the sphere, because the electric field is 0.